So thank you again. For the ones that doesn't know me, I'm at Operation National Lab. I'm a group leader at the National Center for Computational Science that hosts the Frontier Supercomputer. You see the picture here. And I lead a group in workflows and ecosystem services and so on. So workflows, it's a large definition now. So to motivate a little bit the conversation today, I'd like to say where we are now. So right now, workflows have been around for a while, more than 20 years, more than 25 years now. And currently, we used to have workflows that was just in a single facility or, with a single system, like one HPC system or one cloud system. And now we're going into the continuum process that is spanning workflows from, instruments, to the computing facilities, to experimental facilities, and so on. So we have these, now what we call this ecosystem that is connecting these kind of workflows that have heterogeneous systems around. And we keep seeing, more use of AI/ML, integration with HPC, and quantum computing to some extent. So how we are going to work through this convergency? It's right now where we are exploring, and this picture try to represent a little bit where we are with the chaos today, trying to build this ecosystem. I believe, what we want to get into the future, it's more around these autonomous science. That's the term I'm using, but if some people use autonomous discovery, autonomous interconnected autonomous labs, and so on. So there are several terms for the same thing. But the idea is how you integrate all of these different instruments that are an instrument here. Consider computing as an instrument that could be HPC, cloud, edge, and so on. With these different autonomous laboratories that can be robots, but it can also be sensors deployed somewhere, and so on, and everything interconnected and through this distributed data fabric or data mesh, depending on how you prefer to use it. So this is where we want to try to get. It's going to still take a while. Agents that you see on this figure, it's the popular way people are talking about agentic workflows. Everything's supported by AI. Maybe in 2 years, it's going to be something else. But that's we are trying to go towards that. So to motivate, to start the discussions on these, we are talking also about these next generation scientific labs or workflows, autonomous workflows, and so on. And the idea is we had this workshop in November last year that we had a small subset of people from material science and computational scientists, and tried to discuss a little bit how we can enable this kind of workflows. So there is this report out there. I'm not going to spend much time talking about it, but I just want to let you to be aware that we put the same way we do the summits. This is a much smaller report that targets this specific problem issue, how we see these cross-facility workflows operating, and some challenges around that. So talking about DOE more specifically now. So the Department of Energy has several labs, and we have several what we call user facilities. So HPC, that is in the middle, is one of these facilities that we have, but we have facilities with instruments that are doing lasers or producing materials, fabricating materials or isotopes, and so on. So the DOE today actually has 28 user facilities and soon to have 29. And the idea is they are operating by themselves, have been operating for a long time. They work very nicely by themselves. But we got to the point to say, when we try to integrate these different facilities, it becomes a nightmare. So, and even if you look just at the computing facilities, at DOE, we have 3 computing facilities. That it's OLCF is one, another one is at Argonne, and another one is in Berkeley, that is NERSC. And just integrating, moving your code from one computing facility to another, it's already different because you have different software stacks, different policies, and so on. And when you think about integrating with an experimental or observational facility, is even more complicated because you have security issues, barriers, different networks in the middle. And how are you going to connect these systems, or how are you going to, what we call, enable these cross-facility workflows? that might have some computing at the edge. We have a cloud on the open, and you have some HPC system somewhere. It started a huge discussion around the 2020. So DOE, we started this first as an effort called the Integrated Research Infrastructure, or IRI. This is what we call today. And since 2020, they start having discussions with smaller working groups and trying to understand the problem, put this together. And IRI, at the end of 2023, we started to say, okay, we need to design, an architecture, how this should look like, how this integration should happen across these 28 different facilities. And so this is what I call the dawn of IRI. Which always started, we get to know over 150 people from different labs and work to create this blueprint activity. It's a quite long report, but the idea is to analyze the technological, the policy, and the sociological challenges to enable that. Believe it or not, most of the technical part, we know how to do it because it's not hard to do. I say not hard to know. We have the solutions, we know how to do, but then becomes the huge problem is called human. That is in the middle, that is defining the policies, there is the social part, how are we gonna open a port, how are we gonna do a connection, and there is an entire nightmare around that. So the idea of this report was to define this architecture and create now, since last year, what a DOE has, the DOE IRI program. So the idea of the program is to connect the 3 computing facilities with through the YesNet, that is our network for DOE, and with the upcoming the HPDF, the high performance data facility. They are still in the project phase, and hopefully in a few years we're going to have this new facility deployed, all connected to serve, the experimental and observational facilities. And the idea is how we can make all of these seamless connected data would facilitate the researchers. They don't need to think about a software stack or a specific technology, but it would focus into the science aspect. And on that science aspect, they're going to go and move to and let the infrastructure take care of, the deployments, the automated processing of their needs, moving data, and so on. So the program exists today. We are still waiting on the funding part. We are currently using our own funding from the facilities to move this program forward, and we are hoping that once the government decides the budget for the next fiscal year, we might have some initial funding to keep expanding the program to not only have the facilities involved, but also the community involved on the program. So if you look at the blueprint activities, we identified 3 different IRI size patterns. And the idea is how we can classify these different applications. Of course, this is not comprehensive enough, but it was 150 people, and it was hard to come up with these 3 size patterns. Originally, we have 27 of them. But the idea is basically try to divide into workflows that are time sensitive. So it means you need basically near real-time executions. You need a quick response because you're trying to do is to steer an instrument that is running the other side. For example, a common example we see today is a workflow that is connects an instrument to an HPC system. The instrument is producing a lot of data. They send the data, they stream the data directly into the HPC system to train some AI model. And the AI model is going to do inference and inference back to the instrument to steer the instrument to do the next step. And this has to happen in a very short amount of time, because if not, you lose that window. And remember, users or researchers, when they are using these instruments, they cannot use whenever they want. They have an allocation of time that they have to produce their own experiments on that time. So this is one of what the time-sensitive pattern means here. The data integration side, it's basically everything that it's integrating data. So you have multimodal data today coming from different sensors, instruments, and so on. So this kind of workflows that are combining this kind of data, and almost every single use case we have falls into that category too. So it's not exclusive categories, but inclusive ones. And long-term campaigns are workflows that have to run for weeks or even months, to be alive and doing processings. And within that, we have different practice areas. User experience that often is ignored by the community, but how we make the user experience much better. So there is an entire work on this area. Cooperations of resources, so co-scheduling and so on. Security and federated access, it's the elephant in the room when we talk about these things. But we have hope that things are going to improve there, and we're going to be able to solve the cybersecurity issues and access to. And then we have what do we care here about: workflows, interfaces, automation practices. That it's all what we do, what these cross-facility workflows and the solutions, the data lifecycle around it, creating the data, archiving, and so on, and having portable, scalable solutions. And this involves everything related to portability, like containers and so on. So how we are organized as a program today. So the blue side on the figure is basically government and DOE. So how they have their executive authorities and the steering committee that are driving the program on that side. And the yellow side, it's us and the community. So we have the executive subcommittee of IRI that is represented by the directors of each facility. Then they have the leadership group that it's basically pushing the program towards, the accomplish its goals. So it has two representatives from each facility from DOE. So from OLCF in this case, it's myself and SARP, Oro. And we have technical subcommittees that are targeting specific issues to be solved. So right now I have one that is on trying to solve federated identity issue. There is one on the interfaces. And we have the outreach and engagement subcommittee that I'm also co-leading with LiDART. That is how we engage with the applications sites to demonstrate that this program is making progress. And we are also creating user groups. That this idea is bringing the scientists to be able to provide more information about requirements, their needs, so we can better explain what we are developing and be able to understand the requirements of their workflows, so we can create specific technical subcommittees that can address common needs. We don't want to try to solve particular issues, but issues that are shared across different institutions and domains. So going a little bit more down, at Oak Ridge, we have the way we are applying, and enabling IRI is one of the example is an internal funded research project that is called LDRD. So one of them is the Intersect Initiative. And the idea of the Intersect Initiative here is how you're going to interconnect these smart labs. So you have the labs that are have their own microscopes, or they have their robots and so on, that they can be automated by their own. But how you can connect these labs into the edge, from the edge to the HPC. So how we develop these workflows that is going to take data from the instrument, move to the edge, do some pre-processing, from the edge, come to the HPC, train maybe, for example, an AI model, and then we steer back into the edge. So this is so Intersect here was really looking into the communication aspect and defining these abstraction layers to enable these communications and sharing of information. So at OLCF, more specifically, normally when you go to the HPC centers, the way that you connect to the systems is through SSH. So you open a shell and then you start doing your executions. Some of them, several of them have Jupyter notebooks that you can go also and do work. But when we are talking about interconnected different facilities, we need to have APIs, need to be able to do programmatic interfaces to understand how the system is available, and submit jobs, monitoring, set up an infrastructure to stream the data, and so on. So at Oak Ridge, we are developing actually what we call S3M, that is a secure scientific service mesh. And it's basically, it looks for the user like a basic API. But for us, behind this API, we have an entire infrastructure and ecosystem that our resources is going to be connected to this API, and then you can define workflows to use different resources, either if it's a computational storage or any other kind of resources available into the computational facility to stream the data. So data streaming, at least in our facility, is a little bit more complicated than just having, you start a RabbitMQ and say, hey, let me stream things through this or Redis or whatever. It's we need to set up an infrastructure that a stream service can be deployed, and then connectivity, external connectivity can be made between the instrument to the compute nodes. So it's a little bit more complex. So that's why we need to have this kind of this service mesh behind the API to enable that. And of course, everything we need to keep security first in mindset, because at least at Oak Ridge, we have a lot of sensitive data, and we are in a moderate enclave that it's kind of very restricted. So to enable these kind of things, of course, as I mentioned at the beginning, at WCS we have Frontier, that is a supercomputer. It's available on production. So of course, we don't want to be, messing up with Frontier at this point and just be developing solutions that might make things at risk, or even put, some services down. So we have a testbed that we call ACE. So it's the Advanced Computing Ecosystem. And this testbed is connected to IRI right now. So it's part of the entire IRI testbed ecosystem. And the idea of this testbed is we have an infrastructure very similar to Frontier. So initially, so basically you have the compute nodes that have the same kind of GPUs, storage systems, and so on that has in Frontier. But we also deploy different resources into this testbed, like NVIDIA, because Frontier has AMD GPUs, so we have NVIDIA GPUs. These are H100s, but now we're going to get upgrades to the H200s. We have graph cores, we have a 64, ARM64. We are looking into other kinds of storage system, not only the typical Lustre file system, but like things like DAOs, VAST. And the same way that Globus is used to manage data movements around the Frontier and other systems, we also have Globus there, but we are also enabling and exploring how we do the data streaming service. And we have what we call Olivine. It's an OpenShift cluster that is right now is running Kubernetes, and basically is how you deploy a bunch of services into this cluster to be running potentially your workflows or your message queues and so on. And we leverage also Intersect here to enable their use cases. And the idea is through the network, the YesNet networks, to connect these testbed to the entire IRI facilities. So we have some use cases that are happening now, and I just want to show one here that, as you know, AI and agentic AI is on the hype. So we are working on this experiment. This is just a use case with an autonomous additive manufacturing workflow. So on the right side, you have the testbed that I just mentioned. And on the bottom left side, we have a facility that has a 3D printer. And on the top left side, we have a cloud that it's on open cloud to run a few services and has access to both the testbed and the facility with the instrument. So basically here, what they do is, this is a 3D printer, and this 3D printer has to find the best temperature, the best alignment to print whatever they're going to try to do. So what we have is on the test bed, on the HPC side, we have what I call control driver that is running constantly running a simulation and collecting information, receiving information from the instrument facility about what the printer is doing, all the parameters there. And this all comes through a streaming service. So what it does is it keeps doing analysis and trying to find what is the best decision to take to the next step. What is the how you should regulate the printer? What is the best temperature? What is the X, Y, and Z position that you have to move? So, and then when they calculate that, they stream back the best solution to the experiment controller, who is going to steer the 3D printer to go to the right place and do the right things. So today, this is doing still manually. And what we're working right now, and it's coming back to what I said in the beginning, is about the future. So how we automate all of these things. So we are working into putting agents everywhere. So the agents can start to be communicating and taking decisions by themselves on, and even an agent that talks with the researcher to better understand what the researcher is trying to do. So you can automatically steer the simulation with the right parameters to have the correct steering of the instrument. To understand all of these things that we are doing, of course, there are a bunch of benchmarks that you see outside there about HPC, cloud, and so on. But we don't have many workflow benchmarks. So I'm going to do a shout out to Taina, that I know that she's in the audience. This is her PhD work, and she's still continuing to work on it. She developed a tool for creating workflow benchmark suites for workflows. So it's called WF Bench. We keep evolving it, and the idea is, can we make these workflow benchmarks that it's gonna span all of these cross-facility workflows. And I'm almost out of time, so just to finalize, I like this figure to try to summarize it. Again, it's not a comprehensive figure, but it's surrounding things that we are doing. So if you want to get to what we call the autonomous science that is in the middle, of course, today we have the resources that are these HPC, cloud, edge, and quantum, become available. We have the high-speed networks, we have instruments, test beds that are all, by themselves today. So if you wanted to enable autonomous science, we need to look into facilities, APIs, so common APIs. We need to look into federated policies and federated identity. So if I come from one facility to go to another, we can accept and recognize that these users are trustable and we are happy to share resources. So once we have this level, there are all the technologies around that we are working on. And I mentioned workflow benchmarks. We need to work across different agencies, because workflows and autonomous science is not about one single agency anymore, but it's about connecting different agencies like biology, bio agents with computing agents, and so on. Distributed service orchestrations, agentic AI is the hype now. Maybe in 2 years, it's going to be something else. Federated learning with the privacy preserving aspect. Fair workflow components. So it doesn't make any sense we do all of these if you cannot share and cannot find these workflows. Enriched provenance and metadata. So if we're talking about the responsible AI, trustworthy, explainability, and so on, we need this information. And data, high performance data management, because data is key here. It's everywhere and it's flowing across all the different places. So my belief is, once we have all of these set up someday, then we can get to the users and get to accelerated science and scientific results. And with that, I'd like to thank you all and happy to answer questions.